Hi, good morning. My name is Adit, and I will be talking about confidential computing, trusted computing in the cloud. Uh, as a brief agenda, I'll be starting with some of the background, then talking about how this technology actually works, and then finally applying this technology to the transparency ecosystem with witnessing. So back in 2015, Intel released what they call their secure guard extensions and this concept of secure enclaves, where their goal was to be able to allow applications to run sensitive code and use sensitive data on untrusted platforms through a combination of hardware and software features. These secure enclaves were encrypt the memory within the enclave and isolate that data from the host operating system, such that even if somebody has root access on the host operating system, they're unable to access the data within that enclave. So in 2017, Signal was an early user of this technology on the server side. Signal has this feature where you can look up your contacts and check if they are Signal users. But the search space here is pretty small, right? And so it's hard to do this in a privacy-preserving manner. And so what Signal clients do is that they establish a connection to a secure enclave running within servers on Signal's cloud servers. And the enclave is able to provide an attestation, which is a signature over the initial state and this code that's running within that enclave. Once the client verifies the signature and this attestation, the client will only then send over the user's contact data. So with SGX and this initial technology, the access to the data was pretty isolated, only to the application. But this provides a lot of overhead, right? The application needs to tie in with secure enclaves. The developer needs to architecture their application with this use case in mind. And so Intel and AMD came up with this idea of confidential virtual machines, where we increase the trust space to include the guest operating system as well. But this makes it much easier to transfer traditional applications into this confidential space without having to make modifications. So both Intel and AMD have their own implementation of this technology. That being said, I'm going to be focusing more specifically on how AMD does it. And they are broadly similar. So the primary job of confidential computing technology is to encrypt the memory in order to isolate it from the host. When a hypervisor wants to create a virtual machine, it will first talk to AMD's secure processor. And this secure processor is an ARM Cortex-4 chip, a microcontroller running on the CPU itself, but separate from the x86 cores. This secure processor generates encryption keys and ensures that the encryption keys never leave the CPU. It feeds this encryption key into a hardware AES engine that sits between the actual x86 cores and the RAM. When data comes into the CPU, it'll decrypt it before feeding it into the cores, and then as data exits the core, it'll encrypt it before putting it back into main memory. So then another really useful property, right, is to be able to prove and provide proof to a remote party of what software is actually running within this encrypted space. And this process is called attestation. This is a guest-initiated operation, right, that the VM does, and this is independent of the actual cloud provider, right? This process is the same across whatever infrastructure provider you're using. The virtual machine requests an attestation from the secure processor, and the secure processor performs a bunch of checks, and it'll sign a digest over the initial state of the virtual machine. And this is also why it is really important to have the isolation that memory encryption provides. Without having isolation, once you provide an attestation, the host could go and modify what is running in the VM. And so it's not really a useful property to have without the isolation. The virtual machine will then send this report over to a remote party that can verify this, and then it can send over sensitive data such as signing keys or user data. One really fun note here is that this entire system is also just based on PKI. AMD embeds a certificate into the CPU during manufacturing. And this is actually just a standard PKI cert chained up to AMD's root of trust that the remote party can query and get CRLs for, and then use standard X59 tools to validate. So it's important to really look at the threat model here. This is the table of contents of the Wikipedia page of SGX, and 90% of it is dedicated to vulnerabilities. So yeah, it's like we really have to pay attention to exactly what we're trying to protect against here. So this is a select list of threats that are taken from AMD's SEV S&P white paper, which is AMD's latest generation of this technology. So to start with, there is no availability guaranteed by this technology. The hypervisor is always able to shut off the VM and not schedule it and not schedule any CPU time. That being said, we do protect the memory and registers of the VM from the hypervisor and the host operating system. Because we have memory encryption, this protects against offline DRAM access. But AMD very specifically does not consider very sophisticated hardware tampering as part of the threat model. For example, active DRAM corruption is not something that they consider part of the threat model that they're trying to protect against. If this is part of your threat model, you have to protect against it in a different way. And Apple, with their private cloud compute, has done a really good job of considering the hardware aspects and hardware implications and how to protect against those sort of attacks. The last thing is that this technology also does not necessarily protect against architectural side channels. We still have to write constant time crypto code. Stuff like Spectre is still possibly a challenge. That being said, over time, some side channels have been pulled into the threat model that AMD tries to protect against. So stuff like indirect branch protector poisoning is something that a VM can choose to opt into protection for. And this last point is really important when you are considering your specific threat model, right? It's really important to understand exactly what generation of technology you're using, as well as what specific CPU your workload is deployed on. Because as time goes on, more and more of these protections have been built into and pulled into the threat model. Okay, so let's switch gears a little bit. Let's talk about confidential computing specifically in the context of the transparency ecosystem. So I went down this rabbit hole because I wanted to run a witness, but I did not want you to have to trust me, because at the end of the day, I'm just a random person on the internet. And so let's make that very clear, right? As part of our untrusted entities, the main one is actually the witness operator. And notice that the cloud provider is not actually part of this list. Although confidential computing is pitched as a way to isolate your guest from the host, we can also use it and get a little creative to instead shift around who we are trusting. And so to that end, as part of this, Google Cloud Platform is actually part of one of the trusted entities. And this is because I'm using more than just Compute Engine, I'm using some other services they provide. And we'll get into that in a little bit. Of course, AMD has to be part of our trusted entities because they provide the hardware, right? There's no getting around trusting them. As part of this, we're also trusting GitHub Actions to produce container images that are signed with cosign. And finally, we have to trust the application. the application by definition has to have access to perform operations with our keys and our data. And so if we can convince the application to sign the wrong thing or do something that we don't want it to do, then none of the other things really matter. In this case, I chose to use OmniWitness, although there are, of course, multiple witness implementations that we could have used instead. Okay, so let's look at how this witness is laid out in the cloud. So to start with, we have a virtual machine running in a compute engine. And this virtual machine is running Google's confidential space operating system. This operating system is nothing more than Linux, just very much locked down. There are no configuration knobs. There's no SSH access. All the operating system does is it looks at the virtual machine's metadata, pulls a container image, and launches it. If your application is stateless, this is really all you need. But for our case, with witnesses, we do need some sort of state. We need access to a place to sign checkpoints. We need a private key to sign these checkpoints with. To that end, we're using KMS, the key management service provided by GCP. And the KMS allows us to apply fine-grained IAM policies for restricting who can use the key. And this policy is what is going to let us actually restrict use of the signing key to just our witness. So the other thing this confidential space operating system does is at boot, it will first request this attestation from the CPU. I'll send this attestation over to IAM. And IAM will return, once it validates this, this attestation, it will return back a token with a bunch of attributes that we can use to craft that IAM policy. And we can apply a similar set of protections to the actual storage bucket. So let's look at this IAM policy. And this is where things really start to come together. One of the attributes that is provided in this token that IAM will give us is the actual reference of the container. And this reference is a SHA-256 hash. As mentioned previously, the SHA-256 hash is also signed by cosign and linkable to the source code used to generate that image. And so with this policy, we now have a way to link use of the signing key all the way back to the actual source code. And this is a really powerful thing to give someone, because now instead of trusting that I'm running a witness that will not sign the wrong things, you can now actually just go and look at the source code and know that there is an actual link all the way through. Now, finally, there needs to be some way for an outside observer to actually check that all this is configured correctly. And this is not super complicated. What we do is we pull audit data and a bunch of other data about the state of the project within a GitHub Actions workflow, and then publish this into a Git repository. This allows you to know that this data was not changed before it was published. And then an outside auditor or third party can come in and actually validate the state of the project and validate the configuration to make sure that this configuration matches what we expect and matches that entire chain of trust is actually enforced correctly. And this workflow runs every couple of hours to make sure that over time, right, that third party can verify that the project has not been, that the configuration of the project has not changed over time. So the code to this project is open source. You can find it on GitHub. I also have a test witness running in GCP based on this architecture. And you can find the audit logs for that witness also on GitHub. Yep, that's all I have. Happy to open up for some questions.
Hi, Tiziano from Google. Great talk. I really like the trick that you use to dump the policy. Would you say that that's, even if you are the owner of the project, there's no way for you to get around it, like deleting audit log records or anything like that? Obviously, you can change the IAM policy. I assume you are assuming that it will show up in the records, but can you not go and delete those records at all?
Yeah, so the Google Cloud Platform ensures that, or provides this, Google Cloud Platform guarantees that the admin audit logs are read-only and kept around for, I think, 2 years. Okay, so cool. It's a guaranteed platform.
Thank you.
Thanks for your presentation. So more than a question, just like a tip, and maybe we could collaborate on this. So we're working to get Tamago running on enclaves. It already runs on Google Cloud Compute on its own. So I think an application for this is that you can just get rid of the OS layer there, right? So you are now going to need an OS and a container, so you can just run Yomni Witness in the trusted enclave and just get even less dependencies on it. So maybe we should think on that, because I think it would work great with this. But again, thanks for the presentation.
Yes, for sure. There's a couple of other projects that are like doing unikernel stuff, but I'm really excited to see Tamago in this space as well.
Hi, Ed. Thanks for this talk. It's great. My question is, how does the believer trust that the endpoint they're talking to when they're talking to the witness is actually the workload that's reflected by the configuration in the repo?
Yeah, that's a great question. So for witnesses, one nice property we have is that every checkpoint is signed by a private key. And we can get this private key out of band directly via KMS. And so the auditing workflow will actually also pull the public key directly from KMS and publish it out of band. And then you can use that to validate that you have a connection directly to what you think you're connected to.
Okay, thanks.
Any more questions? Okie doke. Well, let's say thank you to Adit again.